Hello, everyone, and welcome to the first session of our first Spring 2026 program for the Virtual Inter-University Symposium on Infrastructure Management. For those who are new to VISIM, this is a virtual symposium that is hosted by Professor Pablo Durango-Cohen here at Northwestern University. Today we'll have two presentations. Chinmay Joshi will be presenting his work on reinforcement learning for pavement management, and Andres Regal will be presenting his work on the freight origin destination synthesis modeling framework. Each presentation should be about 20 minutes long, after which we will take questions from the audience. People can speak their questions or send them using the chat feature. I'd like to point out that this meeting is being recorded and will be made available shortly after. Thank you all for being here, and with that, we can get started with our first speaker for today, Chinmay. He is a recent Master of Technology graduate from the Institute of Technology. Chinmay is currently working in the transportation and asset management domain. His interests lie in the application of optimization and artificial intelligence for asset maintenance, with a special interest in predictive maintenance and stochastic systems. Chinmay, whenever you're ready, you can share your screen and you can begin your presentation.
Thank you, Pablo. Wait, yep. All right. So I'll put this in presentation mode. Thank you everyone for the attendance. I will be starting. Professor Meduri is not here, right? So it's fine. My presentation is on incorporating economies of scale for network level payment management, which is through a reinforcement learning approach. This presentation is for VISIM Spring 2026. So let me start by, introducing what I mean by payment management systems. A payment management system is a systematic approach for operating and maintaining a payment network within resource constraints over a planning horizon. So we have payment assets, which are exposed to the elements, and traffic goes over them, so they deteriorate. Now, when they deteriorate, an agency would want to manage that deterioration. So it will measure what the conditions are that the payment assets are in, and then devise maintenance decision on the basis of that information. So this is the overarching structure that I assume. Now, payment deterioration itself, how can we model it? So in academic literature, you can say, okay, let's ask this question. If you want to know the future, you would ask, okay, do I know the future exactly? Or can I, just give a general idea of what's the most likely future? So if you can predict the future exactly, that's a deterministic approach. And if you can just assign a probability to many different possibilities, then that would be the stochastic approach. So my modeling approach is going to not be just stochastic, but a Markovian decision process approach, which I'll define further. So the Markovian assumption for the evolution of the deterioration state. So a stochastic process means that the future states of the pavement are probabilistic. We only know the probabilities. We don't know what the exact state is going to be. A Markovian process is a process, let's say, this process of deterioration, where if you know the current deterioration state of the pavement, then you can predict what are going to be the probability. Let's say, there is a state 0, there is a state 1, there is a state 2. So each one of those states is going to have a probability. Now, Markovian decision process is going to be based not only on just the current state, but also the current action that the agency is going to perform. So let's say you have a previous time step, a current time step, a future time step, t-1, t+1. So in the previous time step, let's say the state was some st-1 and the action taken by the agency was at-1. In the current time step, we have some state st, some action taken at. In the future time step, which has not happened yet, all you are going to know are probabilities. So what the probability of a certain state of deterioration for your pavement section going to be, that is entirely predicate on the ST and not on ST minus 1, and AT not on AT minus 1. So we've got some literature here which uses similar assumptions that I have taken for my numerical study, which I'll be defining further and further in the future as well. But basically, this is a feature. What are the assumptions, the notation that I'll be using ahead, and numerical understanding of what that notation actually entails. So let's start from the beginning. So pavement sections are, so my entire pavement network is going to be divided into pavement sections. And each section is going to be identical to the other. The only difference between them is how I designate their index. So pavement section 0, pavement section 1, pavement section 2, they are entirely identical in terms of how they behave under certain state and certain actions. But they are ordered. So you in a highway, you start from section 1, then you go to section 2, section 3, section 4. Similarly, pavement states are discrete, and there are only some finite number of states. So here I am taking 8 states with the state S is equal to 1 is going to be the best state, i.e. there is no deterioration, there is no apparent deterioration that can be measured. And state 8 is extremely high deterioration. Probably there is incredible amounts of rutting, incredible amounts of cracking, and it's not really suitable for any kind of vehicle to travel on it. Maintenance decision, there are going to be 4 maintenance decisions. The maintenance decision 0, it denotes do nothing. Maintenance decision 1 to 3 are increasing intensities of repair work. And then transition probabilities are skip free, which means that the probability of you doing an action on a pavement section and the state going from 0, the state going from say 0 to 3 is 0. It can only go either from I to I plus 1 or I to I minus 1. So finally, the planning horizon is finite. If I start from t is equal to 1, I'm going to end at t is equal to 10. That's it. And then the agency stops taking decisions after that. So let's see what the transition probabilities for do nothing look like. Just a numerical example. They look like this. So the probability that the current, if the current state is say 1, if you can see my cursor, if the probability, if the state of pavement section is 1 at the current time step, and we do nothing to that pavement section, then the probability of it being in state 1 in the next time step is 0.6, and the probability of it being in state 2, which is slightly more deteriorated than state 1, is 0.4, so on and so forth. So what is the challenge with with this kind of a set of assumptions? The challenge is, of course, the future is definitionally uncertain. We do not know the future. We cannot predict what the state set for our network is going to be like in the future. If we don't know that, then we don't also know the actions performed. If we don't know the actions, then we don't know what costs are going to be present in the future steps, which means there is no optimization problem to solve. We don't know the parameters. Okay, so, well, what are we going to do? Well, let's just go ahead with firstly defining what this problem is. So we want to minimize total costs over the planning horizon. That's a pretty simple thing to state firstly. And the total cost for a time step t is going to be for each asset, some sort of cost is going to be accumulated to do an action to the agency onto the user, there is some sort of cost involved. So for each asset at each time step, if we add all these costs for all the network that we have, then we get the total cost for that time step. And we are adding across all time steps till the end of the planning horizon. That is the cost that we want to minimize. So the minimization objective here, VST, is to minimize for actions the total present costs where the states are known, plus discounted future costs. Here, discounted means that, for the step 1, we will multiply it by a discounting factor. Or step 2 will multiply it by the square of the discounting factor, so on and so forth. So that, the final, so that as we indicate the future costs, the farther the future is, the less it impacts our current objective. So for the discounted future costs, to actually calculate them or even estimate them, we can't do that because the states at future are not known. Simple as that. So what is the setup of costs? Let's say, for the current time step, how do we calculate costs? So there are two components to this. First is the cost incurred by the agency, which is dependent upon the state set and the asset and the action set. So the action is taken by the agency. And there is a cost incurred by the user as well. So this is incorporated because, the user has to use the asset. And if the asset is incredibly deteriorated, then, the user also incurs a cost. If suppose we do not keep this cost in our calculation, then the optimum approach for an agency is to simply not do anything at any point of time, because not doing anything incurs zero cost, and the pavement sections getting deteriorated doesn't really matter to anybody because there are no users being considered. Okay, but given that the agency and the user costs are added together, means that we have to balance. It's a balancing act. We have to balance both the user and the agency costs. Now, for the user cost, whenever an action is decided on a pavement section, it has the cost, a fixed cost, which is to get things and equipment and labor to that particular section, create a work zone. And then the variable cost involves using, that labor and the material to, do the action particularly. So fixed cost is only dependent on the action because, a particular action requires a particular type of labor, a particular type of equipment. But variable costs can involve anything, the time and construction activities are numerous, maintenance activities, they are not very well defined, sometimes ill-defined. Sometimes you have irregularities among where to do and how much to do. So variable costs are entirely different. They depend on the state and the action. So what is the economies of scale here? Economies of scale is a sort of saving that you incur when a large quantum of similar activities are performed at once. Let's say you are trying to procure a large amount of machinery at once, okay, at a single location. That total amount of machinery per unit would cost you much less compared to if you wanted just one machine at a certain location. This, is an intuitive sense of why these savings occur. But here, you don't need this intuition. You can clearly see that instead of okay, so here what you can see is action 2 is performed on both asset 1 and asset 2. And they are in different states, but somehow the agency has decided that the same action needs to be performed on them. The same work zone is, there is only one work zone here, not two separate work zones for these two assets, which means only a single work zone was required to be set up for these two assets. So the cost of setting up one work zone was saved. So this is the total cost of doing this action on this asset plus, and then we save one work zone establishment cost. So this is modeled as a saving in fixed cost of an activity, which is dependent only on the action performed, not on the state. So the cost in EOS at a current step, okay, can be mathematically derived as follows. Let's say you have payment section 1 to I to n, let's say, and there is a binary variable xiat. So for it's either 1 or 0. It's 1 if action A is performed on facility I at current time step T, and cost at T without considering EOS would be, just the agency cost and the user cost multiplied by whether, it's being performed there or not. And then you just sum it over all the assets and for all the actions at a current time step. This is not considering EOS. When you want to add EOS into it, what I have defined is a linking variable. So a link variable is FIAT, which is 1 if the action performed is equal on asset I and asset I plus 1. So the action performed on asset I is the same as that performed on asset I plus 1, which means FIAT must be linking, which means the EOS is active on that link. So let's say, here, S is equal to 3, A is equal to 2, S is equal to 5, A is equal to 2. So F12, which is asset 1, 2, is equal to 1 because this link is active in EOS. So this is, just definition on what sort of I's it is defined on. It is defined on links, and links are, of course, a number of assets minus 1. Those many number of links are present in our network. So that is how it's defined. So, of course, finally, we have the total costs minus the EOS savings. That's our cost for the current time step when considering EOS. But of course, as you might have seen, that the calculation itself also requires, again, our states and our actions, and this cannot be extended to future time steps. So what do we do? So there is one formulation which was used in Meduri and Madana 2013, which uses randomized policies for future steps while using XIAT for the current step. So at the current step, we always know that the action states and the actions that are performed. But at the future steps, we will just consider the whole system as like one interchangeable blob, and then some proportion of it is going to have action A being performed on it at state S. And then we will just use probabilities, randomized policies to propagate those states further and further based on our transition probabilities. If somebody has a doubt on how this is mathematically incorporated, I have backup slides, but I will not include it in here. So the solution will be feasible for EOS once you go through all the steps. The current step is 1, 2, 3 till 10. So, but at each future time step, solution will be conservative because for future steps you are not considering EOS because you can't consider EOS using randomized policies. So the solution will lack internal consistency. The predicted optimal cost at any current step is going to be greater than or equal to the realized optimal cost, realized after you go through all the steps and end to the planning horizon. So this approach will act as a baseline for our comparison. So let me summarize what's happening here. So we use randomized policies. If we use it at the current step, there is no point using it at the current step. But if we use it at the current step and use randomized policies for future steps as well, it cannot incorporate for EOS, right? If we use X and F at the current step and use randomized policies at the future steps, then EOS SNO, that's what this is called, EOS SNO lacks internal consistency. If we use randomized policies for the current step, X and F for future steps, that's the worst of both worlds. We don't either use EOS nor are we having any internal consistency in the model. And if we use X and F at the current step and X and F at the future steps, we don't know the future, so we have to simulate the future. And this is what the problem statement comes down to. So future costs can be represented as a function of current system state ST and system action state AT. So this is how I'm going to represent it is Q, T, ST, AT. Now, anybody familiar with reinforcement learning would know where I'm going with this. So this is what we want to estimate, this function, Q, T, ST, AT. So the problem statement is a solution framework for maintenance and rehabilitation decisions, which can handle budget constraints, network opportunities, internal consistency between expected and realized costs. And the proposed solution is using reinforcement learning to simulate and learn Q. So, this is how reinforcement learning works. You have an environment and then an agent, and the environment provides ST and reward for a particular action that agent does. And based on that, the agent learns and updates its parameters and, make sure that the reward is maximized. So this, however, does have a lot of problem. You can't use it naively. The set of possible ST, so ST is the state set, system state set, that grows exponentially because, we have for each pavement section, we have 8 different possibilities. And then we have, n different pavement sections. So that's combinatorially, well, it's combinatorially 100 to n to the power 8. So that's, it's not going to be computationally any good. So this is challenging, learning Q, because we have to sample over this such a large state space, okay? And learning over this large state space, like you are going to have very sparse samplings. So it's not going to learn very efficiently at all. So what my solution was to parameterize Q in terms of basis functions. And these basis functions are as follows. So phi TSA multiplied by theta TSA. And phi TSA is just the number of assets in state S and with action A done at time step T. So, any ST I'm given, I will just calculate out the phi TSAs, multiply the theta TSAs, sum them over for all states and all actions. And that is my model for Q, parameterization for Q. Now, there is a problem I saw with this, and I propose an augmentation. BF1, this parameterization, BF1, considers our payment sections equivalent, which is fine, but no weight is given to the links. The links are an important point because, given that EOS is part of our equation. So I added basis functions that also incorporate links. Phi FTSA is basically how many links are active versus how many links are not active, the sum of all of them. So now integrating decision variables into the Q function. So the future costs shall be estimated with in the formulation as this. For BF1, these are our basis parameters, and these are our decision variables. We just sum them over for all the assets and for all actions. BF2, again, we are doing the same thing, but with the link variables included in our formulation. So what we do is, in the reinforcement learning apparatus, we initialize Q at some initializable values. From Q, we sample user range agency cost. Then we go through this whole procedure, and we successively update Q. So there is a hybrid approach, which is called warm starting. Now, you may have noticed that BF1's parameters, i.e. BF1's parameters to be learned, are actually included in BF2. So how about if we learn the parameter values of BF1, then use those parameter values to initialize the thetas in BF2? This approach is BF2 warm start. So I have included many different scenarios, but the base scenario is having no EOS and no budget constraint. So if that's no budget constraint, then it's just assets without any links at all. It's just free assets. Payment section 1, this will have some budget and will follow some deterioration trajectory. Payment 2, payment N, all these. So true optimum for a particular asset is known through backward recursion. So that will act as our benchmark for the base case. For other scenarios, we'll compare USSNO's formulations results. Okay, so we come to the results. It converges the reinforcement learning algorithm, fortunately. And the realized cost to goes from step 1. Those are our comparison results, because that's the objective at t is equal to 1. So a priori expectations are, with increasing EOS, CTGs will decrease due to the savings incurred. A stricter budget will increase CTGs because user cost will accumulate, because due to budget constraints, the most optimal decision will not be able to happen. And then model performance, BF2 should perform better than BF1 because BF2 has more parameters, naively expecting that. And BF2 warm start should outperform both, because it's like using both information from both the models. So here we have the results. There is no EOS in either of these cases, but from left to right, the budget constraint becomes more and more severe. So at the very left, you have no EOS, no budget, and where you can see that all of them perform quite the same, not much of a difference. Although at this scale, you won't see any difference. There is a little bit of a difference. From when budget constraint becomes moderate, you can see that SNO performs the best. BF2 is performing worse than BF1, and BF2 warm start is performing better than either of them. So that one thing is mismatching with our expectations. And for high budget constraint, BF2 again is very, very far ahead, far up compared to BF1. And BF2 warm start is comparable to BF1. On the other hand, here we see something much more expected. BF1 does not perform as well. Here EOS is moderate. BF2 performs similarly to BF2, and SNO is overall still quite better compared to all the RL algorithms. And at very high EOS, of course, then savings dominate practically all the costs, and you get more or less the same results from every formulation. Model performances, you can see, when there is no EOS, when there is no economies of scale saving, BF1 outperforms BF2. Why? Because BF1 is the best formulation for this scenario. It does not consider links, so it does not have spurious parameters in its formulation. Well, BF2 has more parameters that is going to spuriously update, and then it's going to have an increased space which it doesn't need. But when EOS is considered, then BF2 outperforms BF1. BF2 warm start, what happens? Well, in no EOS, of course, initialization with BF1, the solution blocks any spurious updates because it's already at quite an optimum, because it was initialized with an optimum from BF1. And BF2, of course, once EOS is acting, then BF2 just goes from all right solution to the best. So what about internal consistency? RL models should be internally consistent because that's what we wanted, and EOS SNO will not be centered on 0. So this is the difference between predicted and realized cost to go at step 1. So EOS SNO should not be centered on 0. RL models should be centered on 0. And we can see that, yes, indeed, RL models are centered on 0. SNO is not centered on 0. Here, it may or may not be at this scale. It's very hard to know. But this, at budget constraints high, it is indeed showing a massive difference. Now, finally, backward recursion, which tells a very problematic story, because none of the RL formulations are able to reach the true optimum in terms of backward recursion. BF1 is close, and BF2 warm start is also performing at the same level. BF2, we know that it has spurious link parameters, so it shouldn't be able to do anyway. SNO does reach the optimum though. So what's the issue? So the BF1, the pavement sections are equivalent, and hence it's the parameterization is supposed to be valid for this scenario. But there is an issue with the exploration paradigm. See, I did not use true epsilon greedy to make this algorithm converge. I used a modified epsilon greedy, which only considers the top 5 optimal solutions instead of the whole set of optimal solutions. You might have realized why, because the number of optimal solutions, or the number of feasible solutions for this sort of a humongous solution set is not actually itself computationally feasible. So what I did was I calculate the top 5 optimal solutions, and then use the epsilon greedy. 1 minus epsilon, I use the optimal solution. Epsilon by 4, I choose one of the 4 suboptimal solutions. So what are the conclusions? Well, the approach was validated. Q-learning was used to handle present and future constraints while maintaining internal consistency. The important point was complexity does not guarantee performance. More basis functions does not guarantee performance. You have to be pragmatic, understand the scenario, and then choose the parameterization. Only then you can see the performance match. And augmentation does handle EOS better, because BF2 warm start and BF2 both outperform BF1 in terms of when EOS is part of the equation. Limitations, the limitations are fairly clear here, and there are significant potential for improvement in the study. And there is some future work that I've delineated, and I will get back to it as soon as my brain starts working. Thank you for this presentation. So this is my Gmail. Thank you, Pablo, for inviting me to this talk. Yeah. So any questions? I hope I'm okay. So I'm 3 minutes over the time, but if my so I put the dials to you guys now.
Thank you, Chinmay, for a wonderful presentation. And yes, if anyone has any questions for our speaker, feel free to speak up or use the chat.
I have a quick question.
Yes.
So first of all, thank you so much. It was really interesting talk. I hope this is a relevant question, but with Markov decision problems, and then I think with Q-learning too, you do have the Markovian assumption that the future states depend only on your current state.
Yeah.
And so I guess
Yes.
for pavements, is that a realistic assumption, right? Like I don't know a ton about pavements, but what do you think? Like
In
maybe
terms
there's
of
been
now that I've actually been in the industry for 6 months, I actually would have to say that generally you don't even have the information about the current time. Okay, you have
Okay.
to. Probably this is not the case in America, but in India, that's certainly the case, and would probably be for the next 5-6 years before surveillance systems get advanced enough that we can do surveys on a large scale. So it's not a realistic assumption, but it's a working assumption, because realistically you are only going to be able to measure a network at its current time step. If you are able to keep a record of past time steps and the particular parameters that you were able to measure, all the better actually. But this study focuses on this. I feel like it's a realistic assumption to say that a practitioner would want, because a practitioner wouldn't want me to say, okay, you need to have these many different informations for this model to work, right? So that's what I went with.
Okay, yeah, that makes a lot of sense. Thank you.
Sam,
Yeah.
just to add, what people have done in the literature is in some cases just do a state augmentation. where you do capture, let's say, if you feel that there is some history dependence in terms of, let's say, time since the last maintenance or last overlay, which maybe diffuses the rate of deterioration for some years and things like that. Of course, the transition matrices then become sparser, but in a simulation-based setup, maybe it works. But maybe I guess a deep Q learning is what you would need to really capture the Q function more effectively. But since the role of the model which captures the deterioration in this kind of a framework is primarily designed to simulate. I suppose having some sort of a semi-Markov process would also adapt reasonably well if we can get the pipeline to capture the future cost functions more effectively.
Okay, yeah, that makes a lot of sense. Thank you again.
Thanks, Sam.
All right.
Anyone else has questions? Pablo? No. I had a question too.
Okay.
So I saw that you consider cost for the operator that depends on the state and the action, and then a cost
Yeah.
for the users as well that depends
User
on the state. And
state only. Yeah.
so your total cost function would be just the sum of those two costs, right? Like the cost for the operator and the cost for the user.
Yeah. If we do not consider the US savings, so that's, I think, in this slide. No, in the slide. Yeah, this one.
Yeah. Have you considered looking at different scenarios? For example, when a private operator wants to minimize the cost, so they disregard the users, but they have some constraint. For example, they have to maintain the asset at a certain quality on each period,
Oh yeah.
or
That's actually what we started with, but so the reason we did not go ahead with like what is that constraint called? It's called the so a minimum state below which any
Serviceability
NFS can't go.
criteria or something like that. Yeah.
Yeah, so we actually started with that, but then it's just one more constraint. We want the optimization problem, which is finding the actions, the optimal actions, to be as lean as possible. So having the what did you call it again, sir? Midori, sir,
I think he said.
what did you call
Just
that?
some serviceability criteria.
Yeah. Having that in the objective function is much better compared to having it as a constraint. So and it makes particularly if it saves 2 milliseconds for the optimization problem, it's much better in the long term.
Okay, thank you. If there are any more questions for Chinmay, now we'll move on to our next speaker.
All right.
Thank you so much. So now I'm going to introduce the second speaker for today, who's Andres Regal. He is a PhD candidate in transportation engineering at Rensselaer Polytechnic Institute. His research focuses on freight demand modeling, applications of machine learning to freight transportation, and freight transportation equity. Andres, whenever you're ready, you can share your screen and you can begin your presentation.
Thank you, Pablo. Let's see, it should be this one. Yes. So my presentation's on freight origin destination synthesis, and specifically a case study we worked on for a project funded by the U.S. Department of Energy on Interstate 81. And to give you a brief summary of what we will go through, first I will introduce what actually FODS is and demand synthesis as an umbrella term. The model formulation, then quickly go through the case study. So which segment of the I-81 we selected as the corridor, how we configured our zoning system, and the relevant data sources that were necessary for this project. And then for key results, very briefly, the results on the assigned traffic and how the parameters are interpreted, and how this affect the trip length distributions and their interpretations for for the specific needs from our partners in the project. So freight demand synthesis tries to tackle the problem that for any freight demand modeling, say, project or research, you don't really have enough data, and it's usually a major issue because it's not only costly and time consuming, but there's usually a big amount of effort and expense to collect it. But once you collect that data, it's very easy to get it out of date just through spending too much time on it. And usually these types of survey data are especially important for models within a four-step formulation. So in generation, trip distribution, mode split, or traffic assignment. And the idea is, again, we use demand synthesis to infer the demand from relatively easy to collect secondary sources of data, mostly traffic counts and what is available from the FAF as a production and attraction model, which is generally inexpensive to collect, and we can update them as necessary. Specifically, the origin destination synthesis is focused on estimating commodity and trip OD matrices. And we do so by using a gravity model as the centerpiece of our formulation. So in the literature, there's give or take 3 cases that have been solved successfully. So there's the generic commodity case and the multi-commodity case that are based on a gravity model with a set payload or a set tonnage for each truck. And I will present what is a generic commodity case as well. And then there's FODS with mode choice that is the next step forward. What we've added in our formulation is a specific shipment size model to give flexibility on how much or how big the trucks are between ODs. So for a specific OD pair that is closer, you don't necessarily need such a large truck. But if you're going end to end for the whole corridor, you probably use a larger truck. So that should help with the estimation and specifically the spatial distribution of the traffic we assign. The model itself starts with minimizing squared errors, and these are all volumes and traffic counts. So for any link you're considering, you will estimate traffic and just take the squared error. The way we estimate traffic is by using a assignment proportion. So the common way to do this is to use all or nothing assignment. So this is just a binary flag of if for a pair ij of zones, link L is within the shortest path, and then you add up the total effect of the different commodities you're considering. And this is computed, again, with a gravity model with a set shipment size most of the time, but our modeling approach is to focus on a logarithmic-based shipment size model that was estimated from CFS microdata. The idea here, again, you have an assignment proportion. So if you use something like dial assignment or any other route choice or flow splitting method, this can be just the proportion for each link. Then you have a loaded portion and an empty portion, and this is following the Nordman and Van Es empty trips models. And you have, again, a proportion of empty trips here and an impedance parameter for every commodity type. This, generally speaking, is a nice and convex problem. So we can follow gradient-based methods for optimization. So we should have relatively no computational issue as the zoning system grows. Also, an additional benefit of this type of formulation is that we have parameters with real-life interpretations. So generally speaking, the inverse of beta for each gravity model represents the average cost or distance within the area. So when you will see me talk about the average travel time or average cost, it's usually the inverse of the parameter that was estimated. And with the empty trips parameter that is bounded within 0 and 1, this is also strongly related with the percentage of empty trips within our study area. So we will also discuss the percentage, which should be anywhere within 37 to 45%. And this is great, mostly because it provides a sensible check of results. So again, if you have an average cost that is extremely high or even longer than the end-to-end travel time for your zoning system, you know that things are going astray. And the same with if you're seeing more than half of the trips being empty, something is going wrong with your data mostly. Our case study is focused on 725 miles. And here I wrote Dublin, it should be Macungie, Pennsylvania. And this goes all the way into Chattanooga in Tennessee. We're interested in this because Chattanooga and Knoxville as you will see here on the right, this final segment of this is where doubling is basically. It has 4 constituent highways, so you're dealing with effects from I-40, I-75, and I-81. And then this goes all the way up to Macungie in Pennsylvania, where you have an additional effect from Interstate 78. And if you need an extra reference of where's what, DC is roughly around here, and Atlanta is roughly around here. So we have other large freight generators within reach of our zoning system. And we chose these 214 within a 50-mile buffer from I-81 just to be safe and capture interesting effects. As for data, we focus mostly on the FAF and the HPMS. So FAF for anything commodity flow based, and then the HPMS for the traffic counts. These are, for the most part, the same network. We did have to perform some adjustments when some links were considered one-way or two-way, but they were minor things. And again, we get link travel times and traffic counts from the HPMS and the FAF, and then using the county-to-county external flows. Well, we also use them internally for validation, but they serve as a way for us to, at a very nice spatial resolution, merge with our zoning system. And also, just to have a second way of validation, aside from the FAF, we used our own freight production and traction models that were estimated as part of, if I'm not mistaken, in CHLP 44, just to have the internal zoning system, freight production and attraction. So again, the FODS would go from the production and attraction models for each zone, estimate a gravity model for each commodity, assign the traffic, and then compute the error based on the traffic counts observed in the HPMS. In terms of results, this is basically the idea. We're comparing all or nothing against a simple stochastic method. Travel times are basically the same. There's no issue, at least on a generic commodity, on getting it the same, except for a few minutes. Where it differs is that there's a higher empty trip percentage once you consider all or nothing, and then with a smaller tonnage. So using a stochastic method or a proportional flow splitting method, you get fuller trips, and on average, we get a higher payload. So using our logarithmic shipment size, we got anything from 10 to 17 tons between ODs. So on average, it's 14. So it's fuller trips with larger trucks, which is essentially what we want. And then to give you a zoom in into how the flows are, well, the counts are assigned. The problem is that the all or nothing way is giving you paths that are outside the corridor with a significant number of trucks. So the scale is what's showing that this is roughly anything from 8 to 12,000 trucks in these arterials, which shouldn't necessarily happen, but just by computing the shortest path, you have these types of issues. And also there's a large overestimation of traffic along the corridor itself. So on I-81, and the 20,000, which is the maximum, is what is assigned through the whole corridor. The 20,000 trucks as AEDT comes from Knoxville, Tennessee, which is the convergence of the 3 constituent highways, which makes sense there, but along the full corridor, it's probably an issue. Once we start using something like Dial, most of the traffic is centered on the corridor itself. So the arterials do have some traffic assigned, but it's not as significant as before. And most of the flows go through the highway and then come to their eventual destination. And these are paired with the travel time trip length distributions. They keep the same form that you should expect, that there's a hump for the shorter trips and then it tapers off. Both keep it that way, except Dial is a little spikier, as you can see. But the idea is that in terms of decision making, this is all rooted in, we want to know where and how far along the corridor to invest in electric vehicle infrastructure. So the key marker was 400 miles as a point in which, okay, this is the range for an electric truck. How many trips are there, just to make sure the location serves a large portion of the trips, or we capture a large portion of the trips within the corridor. AON captures it as 75%. Dial captures it as 80 to 85%. So again, the difference is probably not as important, but the flow assigned is. So using these trip distributions, we can really inform the the decision makers and the project partners as to where and why to locate these charging facilities or the infrastructure for a distribution center. And to wrap things up, since my presentation is quite brief, FODS is really useful to alleviate data collection efforts, especially when it's regarding freight transportation demand modeling. Our payload models do provide additional improvement both analytically and just giving fuller trips based on larger trucks, which is closer to reality. And then our trip length distributions, generally speaking, aid with decision making. One, where you try to locate parking facilities or charging infrastructure, and you try to capture up to where certain range of vehicles are traveling. And of course, if any potential volume you want to measure for a specific infrastructure, say a bridge or a highway, FODS can easily estimate how much traffic it will probably face. And again, I was brief since this is work in progress and this is all under review, but I'm happy to take any questions and discuss.
Thank you, Andres. Thank you for a great presentation. If anyone has questions, feel free to speak up. Pablo.
Thanks, Andres, for the nice talk. I do have a little bit of a question. When you did the traffic assignment, are you taking into account the induced congestion, or
No.
are you just solving like a shortest path problem?
No, so since it's regional movement, we have not considered congestion as let's say, as a big factor. If it were more localized, say within a few counties, we should use congestion effects, but so far it's just shortest path or just the proportion you would assign without congestion effects.
Professor Meduri.
Hi, Andres. Nice presentation. Thanks. I just wanted to understand the sort of the system boundaries. I mean, sort of what the consistency checks are for the demand synthesis. So, so between the dial and the all or nothing, is the is the idea that the aggregate behavior, the marginal, just sort of the count along the highways are the same across both of them, and it's the other aspects of the distributional, the distribution of the system which then that differs based on the assumptions that you're making? Or is the all or nothing assignment also off in terms of how it is approximating the traffic counts and the basically the HPMS and the FAF data that you're getting? So
it is mostly that it's off. Let's say it's assigning large amounts of traffic to links that shouldn't. Let's say from a rational point of view, it's going outside the corridor in small arterials, and it's also really overestimating the traffic that is actually on the highway of interest, right? So it's basically assigning the maximum possible to the highway that is the shortest path for most of the zones, and from there it splits off into smaller zones. When you use the stochastic way, you do have a more sensible, let's say anything between 10 and 12,000 trucks ADT. That's what we saw from the HPMS, which is a lot more realistic, and then it tapers off as it goes into the 50-mile buffer. So it does give a more realistic idea.
But then within the formulation that you had for dial, are these select, I'm guessing these are, you have information on select links, but not on everything. So are these also getting put in as bounds or as constraints that need to be satisfied within the assignment itself? Or it's not an explicit input into the optimization process, but something that you're using purely for validation after the assignment happens?
It's mostly for validation. Again, the assignment is mostly based on, let's say, what proportion of the traffic from the gravity model would go through that link. We're not adding any constraints in that regard. And surprisingly, the HPMS has a lot of link-based traffic counts. I'm assuming this also comes from some model that fills in the gaps. But generally speaking, we do have a very large sample size, so it is working quite well. We're not specifying any bounds on the assigned traffic.
But then is that something that, I mean, given that your idea is to synthesize something that is realistic and that is grounded in what you're observing, then would integrating that information on the certain links that you have with some, I mean, some measure of how much leeway you want to provide, would that make the synthesis more realistic? I mean, as since you're kind of doing it independently and hoping that it matches, as opposed to guiding the assignment to align the counts better with the links where you observe things to happen, and hopefully that spills over suitably for the other
Right.
links as well.
I
mean, I'm not sure how to
I would-
operationalize it, but I'm just trying to think out ideate at this point.
I would argue that instead of a constraint, the objective being the squared error probably drives it towards a consistent solution.
I see, and that's what you have right now. No, okay.
Yes, so the error is
got
squared
it, fine.
against the traffic counts. So
I see,
it should push it that
That's
way.
I guess that then it would do that. Yeah, right. You're right.
Yeah.
Okay. Thanks for the clarification. Okay.
Vasilis, I don't know if you had a question too.
Yeah, first of all, thank you so much for the great presentation. And it's a very quick question on like the data and mostly on what do you think about it? And you maybe have mentioned it and I missed it, but what do you think about the FAF county-to-county data? Like how good are they for such a study? And in general, like do you think they are useful enough? What did you see if you have an opinion on it? Yeah.
County to county was, let's say, how to put this nicely? It's just a factor to disaggregate the larger zones. So again, if you have however many counties within Ohio, you would have a percentage that adds up to 1 for Ohio, right? For the, let's say, the rest of Ohio zone, and then 1 for the Cleveland zone, and so on. So I guess on the back end, it's more sophisticated. But we tend to prefer our own freight production models just because it's more flexible to the characteristic, let's say, on employment, population density, and so on for each of the zones. It was a good baseline for us to say, okay, it needs to be roughly in this ballpark.
As a proxy, yeah.
Yeah, and from there, if our models were estimating something good, it's a good way to check back to it. But I wouldn't necessarily disaggregate the FAF much more, and I would go for either zonal-based models or census tract models if you want to go at a higher spatial resolution.
Yeah. Thank you so much. We like got our hands into them a bit for like the project that we had, and I had a very similar assessment, but I wanted to see if I was going crazy. So thank you for your take.
No problem.
I appreciate it.
There's another question from Professor Meduri.
Hi, I'm sorry. Just also wanted to wonder, I mean, are there particularly any insights that one could also draw on where you should sample additional data to improve the model? I mean, is there anything in terms of the model outputs which you could also turn around to propose where you should be sampling more to improve the convergence in some respects?
Yes. So I think that could come in hand when you're looking at the TLDs. So if you see the spiking behavior, that's probably where you should look further and try to collect more data, because you would expect it to be a little bit smoother. Or let's say here that is almost a second hump forming, you can probably sample more data from zones that are within that range of each other. But again, aside from looking at it from this perspective, I don't have the other figure, but we do have one where we compute whether the traffic is over or underestimating based on the traffic counts. So if you're underestimating, you can probably collect more data and see if you can figure it out. And then if you're overestimating, you can also add a weight and try to to improve the realism of the solution that way.
Yeah, makes sense. Thanks.
Are there any more questions for a speaker? If not, that concludes our session for today. I want to thank our speakers once again. I think we had two wonderful presentations today, and it was a great session. Thank you as well to the audience members for engaging with our speakers, and thank you to anyone watching us on YouTube. I look forward to seeing you all on the next VISIM session on the first Friday of next month. Thank you.